Okay, today I'm going to take a look at the cylindrical coil transmission gain, S21. This is using the DGA SAQ vector network analyzer from SDR kits. I've used that on a lot of different experiments and posts on the website so far, and particularly in Z11, the small signal AC input impedance for both Tesla coil and TMT systems. That obviously comes from S11, but today we're going to have a look at the, instead of the input reflection coefficient, S11, or the obviously combined with a calibration, we can measure that in Z11, which is what I use a lot, but we're going to have a look at the transmission gain. So in other words, rather than looking at what goes in from the network analyzer and what gets reflected back, taking into account the impedance transformations and the various stages in the circuit. This time we're going to take a look at S21, which this is the input to the system. It goes through, and then we're going to pick up what comes from the output, and then we're going to feed that back to the input. And that's officially S21. Now we don't measure, because it's a gain or transmission. It's transmission from the input to the output. We're not going to use impedance there. We're going to look that in decibels. So Tesla coil measured in this way. It is a passive component. In other words, there is no active gain in this circuit, at least not in the conventional measurement sense that we're looking at here. So from that perspective, if we removed the Tesla coil, cylindrical coil, from the circuit, and we were simply to pass a piece of wire from the output to the input, so for example a jump wire like this, if we were to simply take off this here, take off the output and jump a wire from there to there, once we've done the calibration, we would expect to measure the transmission gain between the output and the input, and that would be in the region of, well, in an ideal situation with no loss in this cable, then we would expect a flat line at 0 dB with no phase change. Obviously there is a very small amount of loss introduced by this cable. It's very short, so for all intents and purposes, the insertion loss of that cable, we would be very much less than say 1/100th of a decibel, so 0.01 dBs. So now this initial part here, I'm going to give an idea of how the circuit's set up, and then I'm going to change the camera perspective so that it, as I've done before, records the PC screen so we can see the kind of results that we're getting. But going back to this system, this is seen as a passive component. Remember that the total wire length of this component is very much less than the wavelength that we're looking at this. Nominally, the series resonant, fundamental resonant frequency of the secondary coil of this coil is at 1.95 megacycles. So that's right in the 160 meter ammeter band. and our connections both to the input and the output are very much shorter than even the wire length. This is a quarter wave resonator, so we're operating it so that it has this wire coming at the bottom of the secondary coil. This is the output of the low end of the secondary coil. This is the high end of the secondary coil. If we just take that off for a moment, and we have a length of wire at the bottom end, reducing the impedance there, that puts it in a quarter wave mode. I can also connect that down to a dedicated RF earth as well. So on the other side I also have a dedicated RF earth at the other end of this wire, which I can connect that to. So for the top end, we have this cable here, and we will look at measurements in two different ways. So I have a plastic ring on the outside of this cylindrical coil. It keeps the spacing correct for the winding, but also acts as a guard, or an insulated guard against the outer copper ring here. So we have a guard or a shield ring as the last turn. There's 23 turns plus 1 on here, and I can connect this outer or this return wire both to the plastic ring and to the guard ring. Now if I attach it to the copper guard shield ring, I'm essentially connecting the top end of that coil directly to the input of the network analyzer. And of course what that's going to do is it's going to load. It's going to load the coil. So this is nominally a 50 ohm input impedance over the band that we're looking at. We're going to be looking at here 500 kilocycles up to 5 megacycles is a normal type of band that I do these measurements over. And if I attach that to the copper, it's going to load the output of the coil. And that's obviously going to reduce its resonant frequency. So we can also take the measurement by putting the wire returning to the network analyzer attached to the plastic outer ring. So in the first case it was attached to the copper, and then in the second it's attached to the outer plastic ring. And that means the wire is very close but not touching the copper guard ring, which means then we're not going to load, or we're going to load to a very low level the secondary coil. We're going to allow it to be a free resonator, and we make that comparison, and we would expect the result that we get to be very close to just the free resonant frequency, the fundamental series resonant mode of this secondary coil. Now the other factor that we also have to take into account here is when we look at a Tesla coil in this kind of measurement. So here we are doing a power, reflection and transmission experiment. That is essentially what we do with a vector network analyzer. So it's we are looking at a one or more port measurement. This is a 2-port measurement that we're doing here. So we are passing a certain amount of power, nominally 0 dBm in here, and we are looking to see how much power we get transmitted back to the vector network analyzer, and also we're looking at what's reflected back down the input as well. So S21 and S21, if you reverse those, then also you could be looking at S22 and S12. But we're going to, that would be the characteristics of full 2-port power characteristics, which is typically what you would use a vector network analyzer for. Now, as I said before, this is a Tesla coil in this measurement is a passive component. So in other words, we don't have a power supply that's attached to it, feeding it power. So therefore, we would not expect to see a gain an overall power gain from the input to the output. It is a passive device. So therefore the amount of power coming out we will expect to be less than the amount of power going in. So we would expect, if there were just a wire connected between the two, that we would read a straight line at 0 decibels. With this in the circuit, then we would expect to see, well, we can see the characteristic here, and where the peak of the resonance is basically just less than 0 dB. So there's a small insertion loss at the resonant frequency. It's not very high, it's a few decibels. But overall, no power gain in this system. Just put that back in. So when we look at the Tesla coil in terms of when we think of a Tesla coil in the way that we use it, we know that Tesla coils can produce very great voltage magnification. So as a result of this resonant coil, the voltage gradient from the base to the top can be huge. When it is set up, depending on the geometry and how it's wound, there's a lot more information on my website about coil geometry, different types of winding, flat coils, cylindrical coils, golden ratio coils, those kinds of things. If this was wound for say arc discharge, or a display, or as a high voltage power supply, there would be many windings on here, and the voltage magnification from top to bottom can be enormous, well into the tens and hundreds of megavolts. Now the cylindrical coil here is designed for this coil, is featured a lot on the website and was deliberately designed as part of the transference of electric power series that I do, and so this has got total 24 turns. Obviously there is voltage magnification there, but the voltage magnification is not enormous, and it's designed such. This is not designed for throwing lots of streamers out into the air, but rather to study the TC and TMT properties inherent when you do transference of electric power between a transmitter and a receiver. So one thing to be careful here, obviously, is we have got voltage magnification, but it is not acting as an amplifier. It's a passive element. So the amount of power that's fed back to the input will be less than the amount of power that we put out. Obviously there is some loss involved, some insertion loss involved in this component. We see the TC as one overall network. So the network, the two-port network, is the Tesla coil. Everything from the input to the output, including the tuning capacitor, the primary coil, the secondary coil. But there will be some voltage magnification, and that we need to make sure that there's not too much voltage magnification. So for the input, but of course, as the voltage is magnified, the current reduces in the secondary coil, so the overall power transferred across the system is less than unity. So just checking the DGA SAQ user manual to check the maximum ratings, which is important for this experiment. So no DC voltages to any of the RF ports, so you must not apply DC voltage to either of these ports, and the maximum safe input voltage into both ports is basically an RF voltage equivalent of 0 dBm, so in other words a voltage into 50 ohm load, or basically 225 millivolts RMS across the measurement range. So in this circuit, because it's a passive Here it is a passive network. We are putting 0 dBm out. We know there is going to be an insertion loss, and we know that the power coming back to this port will be less than that. So according to those characteristics stated in the manual, then we are within the acceptable range. We also know that there is voltage magnification going on the secondary coil, and that is also I determined within safe limit for this device as well. A good way to start off the experiment, if one is unclear, is to put an attenuator in there, say a 20 dB attenuator, and also to reduce the input. So the output of this can be attenuated down to minus 50 dBm. So when one first runs these experiments, you put the power right down low, and then feed it round, gradually increasing, making sure that one is not outside of the characteristics of what this network analyzer is capable of doing. Okay, so that's the setup. The different types of measurements that we're going to do is, well, we have obviously the straight transmission gain, both connected to the copper shield guard ring and connected to the plastic outer guard, and then those are a function of the number of turns on the primary and also of the tune of the primary coil based upon our parallel tuning capacitor. That's a normal 1200 picofarad vacuum variable capacitor, 4 kilovolt capacitor that I use for many of the experiments on transference of electric power. And also because these two coils can be separated, so in other words we can change the coupling, magnetic coupling coefficient K between these by changing the distance, then the experiment can also be done as a function of distance between the primary and secondary. This is arranged so it could go fully in where the coupling becomes very strong. I have these supports on here which empirically from experimenting I've found that the optimum performance for transference of electric power is at about that distance. There's about just over an inch and a half distance between the outer turn of the primary and the inner or bottom turn of the secondary coil. So those are the various different things that we can vary, and what I'm going to do now is I'm going to change the camera position over to looking at the screen of the PC, and then we'll run through the characteristics and the experiment based upon varying those different parameters that we just outlined.
Okay, I've now set the recording onto the computer screen of the VNWA and the DG8 SAQ Vector Network Analyzer software. The experiment is currently set up a 7 centimeter distance between the primary and the secondary, so that's fully closed as I showed early in the video. We've got 3 turns set on the primary and I've got it in balanced. I've adjusted the primary tuning capacitor, the vacuum variable capacitor, to about 550 picofarads to put it in balanced parallel modes, which we can see here if I just take away. So magnitude and phase. That's the input impedance Z11. We can see points 1 and 3 are balanced to 2 parallel modes. Point 2 is the fundamental series resonant mode. I'll just bring back transmission gain 2. So just to show what we've got, we're doing a scan from 500 kilocycles up to 5 megacycles. The blue trace is S21, the transmission gain, and the red trace here is S21 phase. I've also got S11 on here, obviously with the calibration is Z11. So the magnitude of the impedance shown here with the orange trace, and the phase of that, phase of Z11 or S11 on the green trace. Now currently I've got the return wire to the input of the vector network analyzer attached to the plastic ring, as I showed earlier in the video. It's not actually attached directly to the last copper turn at the high end of the secondary coil. So first of all, let me just, this is the Z11, the input impedance. I'm not scanning at the moment. I've taken a scan and paused it. This is very typical for this type of cylindrical Tesla coil. I've shown this a lot on my site before. As said before, it has the 2 parallel modes to 2 series and the single series fundamental resonant frequency here at marker 2. We can see that the 2 parallel modes are at 1.93 megacycles, 2.68 megacycles, and the series mode is at 2.28 megacycles. I've got a 2 meter extension wire at the bottom end of the secondary coil. I don't have that connected down to the RF ground at the moment, but I'm lowering the impedance using that wire so that it is in quarter wave mode. So this is a very typical Z11 characteristics for this form of Tesla coil. I'm going to now, let's have a look at the transmission gain. First of all, let me take away the impedance and we have a look at this characteristic. So this is S21, the transmission gain from the output of the vector network analyzer into the primary coil, and then coupling to the secondary coil, and then that return wire coming off the top of the secondary coil back into the input of the vector network analyzer. And the blue trace here, that is the transmission gain in decibels, and the phase obviously associated with that. And we see, well, first of all, obviously we see this peak here at marker 2. This is obviously at the series fundamental resonant series mode for the secondary coil. That corresponds to, again, 2.28 megacycles. There's associated phase change with that as well. And at marker 2, it's minus 24.65 dB. So insertion loss of almost 25 decibels. Obviously, that is at a real point. It's at a resonant point here. The phase is approximately 0. So that would correspond, if we look at the magnitude, that would correspond to this series input resistance. That's only 3.96 ohms, and that's that's a resistive impedance. So this is very typical for, I mean, this is transmission gain over essentially a resonant coil. Now, also we noticed this, and we've gone into this before in other posts, that the Tesla coil is more complex than just a single series resonator. It has other modes in here. We've talked a lot about the parallel modes that come about. We see that again in S21. The two parallel modes, one from the secondary coil and one from the primary coil. So when we bring them into coupling, into close coupling like this, then we're going to see, and we balance it, we tune it with the parallel capacitance on the primary, then we end up with what I call this balanced mode. And that balanced mode has proven to be quite effective in the transference of electric power, at least over short range, which appears in some of the other experiments that I've done and reported to date. So the complexity of that resonator, which has got both series and parallel modes, is reflected in the transmission gain here that we can see. We go up to this, we call that the series point, and down here to this parallel point, where the currents in the system, the impedance is reaching a maximum, so currents are reaching a minimum. And at that point, marker 4, obviously we go through phase change as well, also showing that this is a resonant mode, and we see we are down at a 90 decibel insertion loss. So the overall transmission of the coil represents a very high impedance to the passage of that input signal at this frequency. Okay, so these are the general characteristics. Now what I'm going to do, first of all, is I'm going to attach that wire to the, let me just take a sweep again, make sure nothing has changed. Okay, so it's stable. So I'm going to, first of all, I'm going to put the return wire onto the outer copper ring. Now we would expect that to obviously load the secondary coil at the tops, and we take a sweep of that. We're going to have to this is off the screen. We're going to have to adjust the reference level, put that at 0 dB. Just move that further on. Get rid of that. Okay, we've changed the reference level to 0 dB at the top of the screen. Now, interestingly enough, now we see that we have actually quite significantly changed this transmission gain characteristic. I'm going to use this marker 2 actually to move to the peak. So this previously was at 2.28 megacycles, and that has now shifted down to 1.44 megacycles. So there's a big shift down in frequency, as essentially we have loaded the top of the Tesla coil. We've basically put a 50 ohm impedance on the top of that coil. The input impedance of the that terminal on the input terminal on the network analyzer is nominally 50 ohms across this frequency that we're working, and that has loaded the secondary coil, reducing its resonant frequency, and also we can see that now that we have a direct connection to the top of this coil, we see that the insertion loss now has dropped down to approximately -5 decibels. So this is what we expect, as we talked about earlier in the video. The vector network analyzer is measuring the reflected and transmitted power in the system. This is a passive element, Tesla coil. Although there is magnification, voltage magnification going on in the secondary, current is also reduced in there, and the overall power gain will be, of course, less than 1. There is no active part to this circuit. It's not connected to a power supply. Power's not being supplied into this circuit. So therefore, in the most ideal case, that is when there's no insertion loss, we would expect marker 2 to be around about 0 decibels. If I just were to connect the output of the vector network analyzer to the input, then that would actually be at about 0 dB, a straight line at 0 dB. So we also notice that that other characteristic, associated to the coil of the parallel mode, is now in the and reflected into transmission gain results. That's now completely gone. So that's been suppressed by loading the top of the coil. So I'm going to put that back onto the plastic ring. So I'm detaching it from the top of the coil, and in effect it's becoming like a probe. So by attaching it to the plastic ring at the top end, the probe is just now very close to the top end. We'll make another sweep of that. And we adjust our marker back up to the top. 2.27. So very close. See if we actually are at the top. There. 2.27 megacycles. And the insertion loss is back to about 24.5 dB. Scan that again. It's stable. And this parallel mode that appears in the transmission gain across the secondary coil is now back again. So what I'm going to do now is I'm going to put this on continuous sweep, and I'm going to make some adjustments, and then we see how these characteristics vary as a result of the different changes of parameters. So if I put this on continuous, that's it. So we're scanning across, and now I'm going to first of all decrease the parallel tuning capacitor on the primary. So I'm in the process of decreasing that. Appears to make very little difference to the transmission gain, just maybe slight shift at marker 2. We see that here marker 2 has shifted very slightly. We put that back at the top again. 2.26 only changed very slightly. Let's add in the input impedance. Okay, we see that is also very significantly changed. So that series point still lined up there. Now at the moment I've gone down to I've wound it right out, the capacitor, so that means it goes down to about 20 picofarad, and I'm going to wind it gradually fully in back through the balance point. Winding it in. There is at the top here. Now the parallel mode due to the primary is now moving down. It's moving down towards this parallel mode here, which comes from the secondary coil. as I continue to go down, that continues to progress. Very little change to the transmission gain. When just go back there a sec, when the primary parallel mode and that parallel point there. There's a point where they coincide. So let's just keep going down. Now we're heading back towards the balance position. So the parallel mode due to the primary and the parallel mode due to the secondary are approximately equal in magnitude. That was about 550 picofarads. Now we keep increasing the capacitance, unbalancing again. As that parallel mode heads downwards, this lower mode is now due to the primary, and this upper one is due to the secondary. They're flipped. We go through that balance mode, they flip over, and that's now fully wound in. And that's fully wound in, that's around about 1200, 1250 picofarads. Again, not that much change to the transmission gain, only a small shift in its center frequency. This parallel mode remains largely unchanged by that adjustment with the primary tuning capacitor. Put that back to the top. We see frequency has now gone up to 2.3 megacycles, and we started at 2.28 megacycles. So that's fully wound in. So I'm going to take that back to the balanced point. I've conjectured a lot in the experiments that I've done that these parallel modes directly facilitate coupling of energy from the primary to the secondary in the LMD mode, which leads to very high efficiencies of transferred electric power between the transmitter and receiver when it's properly tuned, and also when it's driven at the fundamental series resonant frequency at marker 2. So round about there is our balanced position. Put that back at the top. 2.27. That was where we started when I changed the probe at the top end back to being on the plastic. A nice sharp parallel mode here as well. Marker's not quite lining up. That was because the shift of probe that I make. I will just put them approximately in the right position. At this point, there we are. There. Okay, so very back to where we started, or very close to the starting point. So I'm going to pause that. I'm going to take away that first of all, and I'm going to pause that, and I'm now going to increase the primary windings up to from 3 to 4. So that's now 4 primary windings Let's do a single sweep. Okay, so not a great deal of difference to the series resonance mode. Actually, what I'll do is if I put it back on 3 and I take a single sweep, obviously you see there's a big change here, but we can capture some of that. So I'm going to move S21, copy S21 to memory 1. I'm going to add a trace on here. Let's turn those on. Let's add another trace. The memory 1, we're going to switch that to S21, and we'll measure that in decibels. Yeah, that's the black trace. So we can see how this is affected. I could get no, that's the maximum number of traces. So let me take off these ones. I've got a store now. The black trace is for 3 turns of the primary. This is how the transmission gain looks. So if I now move it back to 4 turns of the primary, take another sweep. I was expecting that to stay still. Oh, I know why. I need to move that to memory 1. Okay, so let's just let me copy that to memory 1. Now I can move it back to 4 turns of the primary, take another sweep, and now we can see how that's changed. That was the point of doing this. So we can see as a result, so the black curve shows in decibels, the magnitude of the transmission gain, and the black for 4 turns, and then the black curve shows it for 3 turns. So we see as we've increased that primary effect, this has been a significant change in this parallel point. Here, it's shifted down considerably in frequency as a result of adjusting the number of turns. So I'm now going to move it down to just 2 turns. So that's now on 2 turns. We scan it again. Interestingly, that was actually 2 turns in the middle. That's actually in the 2 middle turns. And we see it has shifted back up again, but not as far as the 3 outer turns. Let's move it down to 1 turn. This is 1 outer turn. That point seems to have disappeared completely. That parallel mode has disappeared completely. Frequency shifted down to 2.16 from 2.27. 2.16, 90 kilocycles. But the interesting part is this area now, and that mode, that's completely gone. We're just using 1 outer turn. Going back to 3 turns, which is where we started. almost back to exactly the same as where we were. So the changing the turns of the primary makes considerable difference to this mode here, what we're calling the parallel mode, and that appears to be coming primarily or have very, very strong influence from the primary circuit. So being associated with this parallel mode in the input impedance. These appear to be associated with each other, which will be, if I go back to sweeping, it would be quite interesting to see. Actually, let me modify it first. If I put it back to 1 turn and put that on, yeah, now that parallel mode is missing from the input impedance as well. Or it's right up off the top here. No, it's not even off the top. It may be further off the top here, but it just doesn't appear where this is obviously from the 3 turns. Yeah, it is missing. It's missing in the input impedance. This one here, this small one here at the bottom here, is due to the secondary coil, but the parallel mode from the primary is gone. It will probably be a much higher frequency off the top here. That's just with 1 turn. So if we just go back to 3 turns, put it back on continuous, there we are. So this peak here at marker 3, parallel mode from the primary, and this also appears to be connected with this characteristic in the transmission gain as well. Whereas this characteristic here is associated with the series fundamental resonant frequency, which is predominantly based on wire length in the secondary coil. This peak here associated with the primary mode of the secondary coil. Good. Okay, let me turn that one off for the moment, and I will leave the input impedance, just check the phase, is what we would normally expect. Now what I'm going to do now is I'm going to leave that scanning, and I'm going to move the coil, the secondary coil, away from the primary coil. So I'm moving it away. We can see obviously the changing characteristics in the parallel modes. Okay, that is a distance now of 20 centimeters. We were first at 7, then we were at 20. Now we're going to keep moving further away. So that all these modes starting to really collapse onto each other. See that? Just slightly. That's 30 centimeters separated between the two. And those modes are really started collapsing together each other on frequency. So as the coupling, the magnetic coupling coefficient K between the primary and the secondary is reducing, so the spacing or the interaction between those different resonant circuits and modes between the primary and the secondary are now really starting to become distant or become less coupled. We go a bit further. I'll take that out to 40 centimeters. And out to 50. That's at 50. The secondary coil is starting to go out of the vicinity of coupling between the primary and the secondary. So I'll move it out to 60. That's at 60. We can see now that they're almost out of coupling between each other. If I was to go to around about 70 or 80, takes the coupling out completely. Let me take that. That's as far as I can actually move it this time. That's at 75, and we see that's almost, they're completely out of coupling here. Just a tiny influence being, a tiny bit of signal being passed from the primary to the secondary and back into the input of the vector network analyzer. This parallel mode from the primary now is very accentuated, it's very clear. We can't see anything from the secondary. There's so little coupling between the two. That's at 75 centimeters distance between the primary coil and the secondary coil. So now I'm going to move it back down. Okay, moving them slowly, sliding them slowly towards each other. Coupling is starting to come back. It's about 50 centimeters. K is increasing very slightly. The series and parallel modes starting to strengthen. They start to split. About 40 centimeters. Starting to become quite developed again. That's it. Now we properly start seeing those modes splitting out. $20 centimeters. 10. Back to 7. And we're back to the balance condition where we started. So that really does show the effects of the coupling going on between that primary and that secondary, and as you start to distance them, how those modes start to collapse, all start to collapse together onto each other as the two coil systems, the primary system and the secondary system, move. The coupling between those two systems is reduced, and in effect they separate, or they collapse onto each other, and as the coupling increases as you bring them back again, so the interaction between those two circuits, then the modes start to separate. Right back down to where we are in the balance mode with the primary tuning capacitor set to balance those parallel modes. again, we're back to the series, the highest point in the transmission gain, that series resonant mode at 2.27 megacycles, and with insertion loss again of about minus 24 dB. Just add S21 here. Good. I think that shows a good insight into the characteristics of how this coil, and we've now added S21 to the work that prior has been done on the input impedance, Z11 coming from S11, which has shown so much about the characteristics of a Tesla coil. We will be going to another stage in a subsequent part where I will look at the transmission gain S21 for the TMT system. This is an individual Tesla coil first of all, and then we will go and have a look at the TMT system, both in the balance condition and with a load on the end. So if I put our reference line back in, I'm going to turn off this just to make it easier to see things again, and I'm going to put it back onto the copper top turn of the coil whilst it's scanning. We see what massive change that is. We see how far that has moved away now. Loading that secondary coil. This time I'll use marker 1 since marker 2 is set at that peak. Obviously we don't have the same insertion loss now. We are connected directly to the top of the secondary coil. Insertion loss is much as it was before, around about 5 dB. And down to about 1.44 megacycles again. So massive change in impedance, which we would expect because we are loading the top of the coil. By loading the top of the coil there, we are changing enormously the quarter wave properties of that coil. We are adding both wire length to the top of that coil, and also, of course, the input impedance, and of course the input impedance of the vector network analyzer itself. Okay, good. Let me just put that back on that outer plastic rim. Positioning there makes a difference. Where we position it on that plastic. We go back. Good. And that is the S21, the transmission gain of a cylindrical Tesla coil with characteristics as I've shown, and I'll be looking at some of those results in more detail in the write-up. And as I said before, the next part of this will be to extend that transmission gain over to a full TMT system with a transmitter, a receiver, and a single wire in between. Great, that's that for this part.